Okay, well, thank you very much, Caitlin, and apologize for yesterday's technical issues, but happy to present today. So my name is Antoine Decaux. I'm a graduate computer scientist from Australia, and I recently graduated with a major in machine learning. So the picture in front of you is basically desert with a Tuareg who is a desert nomad in central North Africa, going through the desert with his camels, with the sun behind him. So this is kind of to represent the life that I do have, which is that I'm walking through a visual desert, but I try to pick up on the signals, such as those that the sighted people can see on the sand dunes. And those sand dunes kind of give a lot of information, about the direction of the wind, about the height, all of these things can be picked up. And this presentation is to show that it can also be picked up by sound.
Slide 2, going into space.
So we're going to immediately just jump off and go into space. And I will show you the introduction of the app I have been working on, which is called Astrios.
Bill 1 of 1.
Good afternoon. I see this is your first time on board the ISS Astrios. I am your artificial help agent, Leah. Let me give you an overview of how the onboard system works. Loading training module. Please wait. You are currently located in the Southern Aegean. Loading ephemeride. I have now loaded Saturn into the system's targeting display. You should be getting feedback if your SMC kit is version 7 and above. This is the Tactile Object Tracking, or TOT, subsystem. Perfect. Now double tap to zoom in. Magnifying. You are now looking at Saturn in its actual position in the sky through the telescopic telemetry subsystem.
Slide 3, NASA Horizons.
So this is basically Astros, and this is just a tutorial introduction just to onboard people who don't know how to use the app. But to give you some context, this is an augmented reality app that started in a garage. And the question I asked with my business partner, Jake, we're both engineers, we love to create things and we spend our time doing that. And the question back then was, well, how can I actually listen or understand where the solar eclipse is, or understand where the moon is? And from that question, I started digging into various things such as the NASA Horizon system, which lists a whole bunch of objects which are in the solar system. And I put it into a 3D audio space and kind of attached this way of, understanding how to get there by using the same systems that cars use, except that in this case, it's in 3D space. And I sort of kind of got really deep into this, into this journey, and that kind of led me to win the NASA Space App Challenge in Brisbane. Our app got covered across the world, physics magazines, Naked Science. It went through multiple channels. And so at that point, I thought to myself, well, maybe this is something really interesting, because on top of having the media coverage, I've had thousands of blind and visually impaired people contacting me and telling me that they did not have an idea where all of those stars and constellations, all these objects were located.
Slide 4, tactile representation of graphics.
This is
Bill 1 of 1.
Querying satellite.
So here, I'll show you another instance.
Loaded ISS.
And this is the ISS
Magnifying.
that is being shown. So as a blind person, I'm able to actually touch the ISS and the different, parts of it, the panels, by using haptics on my iPhone. So, yeah.
Slide 5, L1L4 orbiting satellites.
I went further into the madness of trying to make things accessible after, all of the requests and recommendations coming from those visually impaired and blind people like myself. And I went further and tried to figure out if there was a way to represent all of the objects which are in orbit around our planet, which are currently censored at about 29,000 different objects between science, spacecraft, boosters, amateur radio, even military. All of this is actually being accessible to people who may technically want to download that data. And I make this possible through haptics through the app.
Slide 6. Osiris REX mission in Bennu.
Here, it's also the fact that the app
Build 1 of 1.
is dynamic, meaning
Querying
that
spacecraft.
this is back in the days when OSIRIS-REx was going around Bennu, so an
Ephemeris
asteroid.
loaded
OSIRIS-REx.
for
It went through a mission, and you could look through it in the
OSIRIS-REx.
sky, and then you can zoom into it by
Magnify.
tapping on the screen, and then you will have Bennu in front of you. And when you change modes, you can literally
Slide 7.
feel Bennu with your fingers. So there was this interesting anecdote. I spoke to the NASA senior navigation engineer, and I said, "Well, does Bennu look like a lemon?" And he said, "Yeah, absolutely." So that was a revelation.
Build 1 of 1.
Corona Borealis.
Now I'll show you constellations and how they're being
Magnified.
designed, and I will put the sound up a bit. So we're in a very quiet constellation, but you can hear
Minor
those
mode.
chimes. Those chimes are basically the major stars and some of the minor stars, and you would be centered in the middle of this
Exoplanet
constellation,
mode.
and you'd be able to hear all of those stars literally around you.
Slide 8. 1.8 billion stars.
This app basically monitors 1.8 billion stars, which come from multiple systems, including Gaia and a few others. And so one of the big aspects of this project, as I have come through afterwards, is that it's spatial sound. That means if I have a surround system, I could play that information around me.
Slide 9. Hunting for exoplanets.
For instance, when we
Slide
go
10.
for
Entering exoplanet discovery.
we go into
Build 1 of 1.
Corona
exoplanet discovery.
Borealis. Buddhist. Magnifying.
So this is the same information, but we can use the signals from the audio in order for us to better understand the data that is available through all of those scientific products coming from NASA,
Minor mode.
ESA, and other space agencies.
Slide 11. K10. A known exoplanet host star.
Now, I'll show you, I'm trying to go pretty quickly because I'm very limited in time and I have so much to show. But this is an interpretation of those of you who are scientific and know a bit of mathematical notation. This is putting a time dimensional data into frequency. And this is the way I started my journey to making audible scientific information.
Build 1 of 1.
So this is basically the frequency split of looking at a star. So let's say you point a camera at a star and you just keep looking at it for a very, very long time. And then you sort of understand the different cycles of light emission coming through. You split those emissions into different channels, and then you compose them back. So for those of you maybe who have a keen ear, you might have heard a small dip in the sound. That basically means that an exoplanet is transiting the star. It's a very different way of listening to things, but I will show you also one of the classical ways of listening to data that is, that can be used basically for scientific purposes. So on my journey, I continued on.
Slide 12. Going even further.
And going even
Build 1 of
further,
1.
I started making galaxies and simulating galaxies visually on this video. Unfortunately, I haven't placed the sound yet.
Slide 13. Black hole catalog.
But also I've added
Build 1 of 1.
black holes. This is a visual of the black hole. I'm still trying to figure out how to best sonify a black hole, but I've got some ideas there.
Slide 14. The Holman journey.
And to continue my journey to really understand astronomy, because I have a computer science background, I actually applied for the Holman Prize in 2019. And my project was to go across the world and interview multiple scientists, astrophysicists, engineers, satellite engineers, and others, cosmologists.
Slide 15. Podcasting with live Q&A.
Basically, by creating a podcast, which is almost like a video-based literature review, with the same question posed at the end, which is, well, how to make this accessible?
Slide 16, following the footsteps of Sir James Holman.
And in some ways, I was also following an adventure in the footsteps of Sir James Holman, who was a blind person who navigated the world on his pony and a white cane. I sort of took that and went across Africa, the Middle East, and Israel, and ended up in Kurdistan, at which point COVID hit, and I had to scurry back home really quickly before all the gates closed. And at that point, I was back at home. I had my second leg of my journey, which was canceled due to COVID. And I thought to myself, okay, well, I need to continue on this and create a scientific version of the app that I just showed you. Now, this is what I'm going to do.
Zoom.us Xcode. Xcode.
And this is basically the macOS version of Astros, but it's much more scientific, and it uses standardized tools such as FITS file formats.
Cable no bill succeeded to me. 3-minute warning.
Visualizers.
Application. Sensor image. Dsonic. Window. Search. Space with application Dsonic.
So here you have basically the sky, and this is Cassiopeia showing in front of you. I can actually understand how Cassiopeia sounds and feels.
Viewport.
So for those of you who see the cursor is mapped to the actual location and the sound of Cassiopeia, which is in the middle over there. And as I move around, I'm actually moving in 3D space. 3D space meaning that my head is actually intersecting the galactic plane, and the top of the screen is actually ahead of me, and the bottom of the screen back of me, and left and right is left and right. Now,
search Andromeda.
This tool allows you to look for any object in the sky. So let's say I place Polaris. I look for Polaris.
Loaded.
And now it's loaded. And now I can listen to the environment around Polaris. I can also feel it. I can, unfortunately, haptics cannot be shown here, but I can actually feel the different stars around Polaris. I can also change the actual notes. And this all actually happens in 3D space. Unfortunately, my screen reader has turned off. I'm going to turn it back on.
VoiceOver and Dsonic. Window. Viewport has keyboard focus. Search. Polaris. Content selected.
So what we're going to do is we're going to search for Kepler 12.
Kepler. Kepler 12. Selected.
Loaded.
Search.
Oops.
Zoom.
Excuse me. I'm really sorry about this.
Keynote. Application.
I think I'm running out of time, unfortunately, but the app currently is still in development, but it has gotten a winter research project grant this year, and it's actually going to continue with a summer research project grant. And we're going to make this public at the end of the summer semester because it has been in collaboration with the Dark Energy Survey team at the Fermilab. And this will allow people to do a lot of things. Unfortunately, I couldn't show all of the features in this demonstration. But just to finish this off, 3D spatial audio is very, very useful for people who are blind like myself, and it can be used in the context of many scientific endeavors. One of the richest ones being astronomy. I fully advocate, the ability for people like myself to access this information and to do something about it, because in terms of the citizen science space, this can really, really help a lot of people on both sides of the equation, the scientists and the citizens, to better understand the information, and for the scientists to get some help on identifying phenomena and objects around our universe. Lastly, if you would like to get in touch with me, have some discussion, maybe collaborate, maybe help me try to diffuse this information further, I am Yuma, and you can go to astrios.space and you can look at the website, download the app, and you can go to the contacts page and get in touch with me. All right, thank you very much.